In the last section, we talked about functions. In this section, we are going to define one-to-one function. A function f from a into b is said to be one-to-one if whenever x1 not equal to x2, then f of x1 not equal to f of x2 for all x1 and x2 in A. In other words, if the pairs x1 comma f of x1 and x2 comma f of x2 are in F, the subset of the Cartesian product of A with B, with x1 not equals x2 implies f of x1 not equals to f of x2 for all x1 and x2 in A, then f is a one-to-one function. Alternatively, a function f from A into B is one-to-one if f of x1 equals f of x2 implies x1 equals x2 for all x1 and x2 in A. Let's look at an example. Suppose A is a set with these three elements and B is a set with these three elements, and the function f from A into B is defined by this formula. Then f is a one-to-one function from A into B because the subset f of the cross product, the Cartesian product of A with B, is this set. The -3 is -3 squared, 9, this is the pair, and 0 comma f of 0, which is 0, and 2 comma f of 2, which is 4, and f of -3 equals 9. So these three are the ordered pairs, the subset of A cross B. This is a one-to-one function. Since the first elements, we have the different second element for any two pairs. Let's look at a non-example. Let A is a set with these four elements and B is a set with these three elements. And suppose f is the function from A into B as defined earlier, then f is not a one-to-one function from A into B because even though -3 is not equals 3, but this doesn't imply that f of -3 is not equal to f of 3. In fact, these two numbers are both equal to 9. Alternatively, f of -3 is equal to f of 3, but -3 not equal to 3. So this function here defined on A to B is not an example of a one-to-one function. Let's define an onto function. We say a function f from A onto B if for every y in B there exists an x in A such that f of x equals y. It means for every element in B there exists some preimage in A such that f of x equals y. Let's look at an example. Let A is a set and B is this set. Suppose A is a function as defined earlier. Then f is a function from A onto B because, for example, let's take 4. So for in B, there exists some element in A such that f of 2 equals 4. Similarly, for the case of 9, in B, there exists some element in A such that f of negative 3 equals 9. Now let's look at a non-example. Suppose A is this set, B is this set, and f is defined as previous. Then f is not a function from A onto B, because there exists some element in B such that there doesn't exist any element in A such that f of x would be equal to 1. So this is not an example of a onto function. Inverse function. If f is a one-to-one function from A onto B, then we define f inverse by this. So f inverse is a set of all ordered pairs y comma x from the Cartesian product B cross A such that f of x equals y. Then f inverse satisfies the definition of a function. So f inverse is a function from B onto A. And this is called the inverse function of f. Let's look at an example. Suppose A is this set and B is this set, and f of x is defined to be equal to x squared. Then f is a set of ordered pairs like this. So negative 2 comma f of negative 2, which is 4, 0 comma f of 0, which is 0, 3 comma f of 3, which is 9. So f contains only these 3 ordered pairs. So if we define f inverse this way, so 4 comma negative 2, which is obtained by switching x and y here, and 0 comma 0 and 9 comma 3. So this is a function from B onto A, and this is called the inverse function of f. Composition of functions. If f is a function from A into B and g is a function from B into C, then the function g circle f from A into C, defined by this, is called the composition of g with f. So g circle f, the composition of g with f, contains all the ordered pairs x comma z from the set A cross C, where z should be calculated by using this formula, which is z equals g of f of x. Let's look at an example. Suppose A is a set with these 3 elements, and B is this set, and C is this set. We also suppose f is a function from A into B, g is a function from B into C, defined by these 2 formulas. F of x equals x squared, and g of x equals x plus 1, respectively. Then f is the subset of the cross product A cross B, containing these 3 pairs only. So negative 2 comma f of negative 2, 0 comma f of 0 and 3 comma f of 3. Similarly, G is the subset of the Cartesian product of A with C. So 0 comma G of 0, 4 comma G of 4, 9 comma G of 9, following this definition. Then the composition G circle F from A onto C is given by the formula as given in the definition. So let's calculate the Z's. For example, G of f of negative 2 is same as G of 4, since f of negative 2 is 4. So G of 4 by definition is 5. Similarly, G of f of 0 equals G of 0 equals 1, and G of f of 3 equals G of 9 equals 10. Therefore, the composition G circle F is the set containing these three ordered pairs. So remember, this is G of f of negative 2. Similarly, this is G of f of 0, and this is G of f of 3. And this is illustrated in this figure. So f is a function which takes from negative 2 to 4, from 0 to 0, and from 3 to 9. Similarly, G is a function which takes us from 0 to 1, from 4 to 5, and from 9 to 10. Therefore, the composition takes us from negative 2 to 5 by following this direction from negative 2 to 4 and 4 to 5. Similarly, the composition takes us from 0 to 1, and from 3 to 10. This is the composition. Note that in general, G of f not same as of G. For example, in the left hand side, this is function from A into C, and in the right hand side, this is a function from C into A. If f is a one-to-one function from A onto B, then it can be shown that f inverse of f of x equals x, and f of f inverse of y equals y for all x in A and for all y in B. Hence the name the inverse function. Let's look at an example. Suppose f is a function from R to R defined by this formula, f of x equals 2x. Then f is a one-to-one function from R onto R. Please verify this. Then the function f inverse from this R to that R defined by this formula for all y in R, then f of f inverse of y equals f of y over 2 equals 2 times y over 2 equals y. And it's true for all y in R. Similarly, f inverse of f of x equals f inverse of 2x equals 2x over 2, following the definition, which is equals to x, and this is true for all x in R.